Okay, welcome everyone. The plan for today, first part is I'd like to discuss maximum likelihood estimation. This is a technique for understanding probability distributions, and it builds off of the exploratory data analysis that we were doing before while being more quantitative. You can think of maximum likelihood estimation as a little bit like a regression, kind of by analogy, regression for probability distributions. So in a regression, like a linear regression, you might have some data like this, and you're kind of trying to fit a line that goes through the center of the data. And the way you would do this fitting is you would kind of try to estimate the values of the two parameters, m and b, for a simple linear regression by trying to minimize the difference between the data points y values and your line of best fit. You can imagine doing the same thing if you want to fit a probability distribution. In this case, you would have different values of x, and then you would have their probability as your y-axis, and you would have some histogram. I'm not going to draw it extremely well. And you want to somehow estimate for a probability distribution what is the function that kind of best goes through those points. You could actually do this as a type of regression where you're trying to actually minimize these differences, these least squares, and then the parameters that you're fitting are somehow related to the probability distribution. Here the theta is meant to capture whatever those parameters are. Those could be the mean and variance of a normal distribution, for example. What separates maximum likelihood estimation from just simple regression is that it explicitly incorporates the fact that you're using probability distributions. So maximum likelihood estimation, or MLE for short, really focuses on data coming from probability distributions. Okay, putting things in a little bit of a concrete foundation, let's imagine for now that we've conducted some experiment or some process has happened through which we've gathered some data. And by data, we'll just keep it pretty simple. We essentially have a list of values. And we can just think of these as x1, x2, all the way up through xn, just numbers. They could represent, for example, the heights of a bunch of subjects. So that's our data. And suppose also, as part of this fitting procedure, we have a candidate function, which I'll call f, that represents the probability density, or specifically the probability of these data. What do we mean by this exactly? We can consider the probability of the data as essentially being a joint distribution over all of our observations. So what's the probability we get this value for x1 and this value for x2 all the way up to this value for xn? Oftentimes we also assume that this distribution has one or more parameters that we'll represent with theta. Theta, for example, if you have a normal distribution, it would actually represent two parameters, the mean and the variance. Oftentimes the mean is written as a mu, and the variance is written as a sigma squared, so mu and sigma squared. We might be looking at simpler distributions that may only have one parameter. So we just generically represent the set of parameters for the probability distribution as theta. So what this is giving us is the joint distribution of all the data given values of the parameters. Recall what we have for linear regression. there we've gathered some data, and the goal is to figure out the parameters, for this case m and b, that best fit this line. In our situation, for maximum likelihood estimation, what we're interested in is finding the best parameters for the probability distribution. So that's our goal. We're going to try to estimate these parameters. Right now, the probability distribution is conditioned on those parameters, so we need to somehow figure these out from what we've already gathered. Okay, so how do we end up doing that? How do we figure out what the value of the parameters should be? First thing we should do to make progress is make things easier. Specifically, we'll assume that each data point is independent. Second, that all data points follow the same distribution. And when we put these two factors together, we're essentially assuming the data are IID. So the list of X's are IID. This lets us simplify our joint distribution. So instead of having all of the complicated dependencies between these data points, given the theta, instead we just have each individual data point in its own distribution. And because they're independent, the joint is then just going to be the product of all of these individual distributions. The first part, each one occurs independently from the other, means that we have this nice factorization. This joint distribution becomes this product. And the fact that all of them follow the same distribution means that they all have the same f and they all have the same parameters theta. So we're just left with a big product. When we put all of this together, what we're essentially looking at is the probability of all of the data given the values of these parameters. So if you tell me the values of theta, I can then say the probability of getting all of this data is some number given by this function. But that's not what we want. What we want to say is, okay, here's the data that I've received. What's a good value for those parameters? We need to somehow flip these around to start answering questions. And that's what maximum likelihood estimation does. What maximum likelihood focuses on is what they refer to as the likelihood, quote unquote, of the parameters given the data, which I've indicated here in blue. Is flipping these two things around, and that's usually written like this. They've got a kind of fancy script L for the likelihood, and then you have the likelihood of the parameters given the data, which I'll write out like this. And the amazing thing in maximum likelihood estimation is to simply equate these two expressions. And that might sound a little bit crazy if you're used to working with conditional probabilities. You can't just flip them around like we're doing here. And the argument, and I'll get into a more rigorous treatment of this at the ending, but the argument here that allows us to equate these two is to claim that this thing here is a probability, but this thing here is something mathematically different that is referred to as a likelihood. And even though in everyday speech, likelihoods and probabilities and odds, they're all kind of used interchangeably, mathematically they tend to have different meanings. Maximum likelihood's goal is to then make that function as big as possible. This is the maximum in maximum likelihood. meaning specifically we want to find a particular value or values of the theta, called theta hat, that maximizes the likelihood. And this value is referred to as the maximum likelihood estimator, or the MLE estimator, for the data. And we'll see how to actually go about doing this next.